Today we shall discuss about series resistance microammeter. High DC voltages are usually measured by a very high resistance, that is maybe a few hundreds to mega ohms. In series resistance microammeter, this is a series resistance microammeter. A protective device is connected for that. Only the current I flowing through the large calibrated resistance R is measured by the moving coil ammeter, microammeter. The voltage of the source is given by V is equal to IR. The voltage drop in the meter is negligible as the impedance of the meter is only few ohms. Meter is only few ohms compared to few hundred mega ohms of the series resistance. A protective device like you can see a protective device is connected for that. A protective device like a paper gap, a neon glow tube, or it may be Zener diode with a suitable resistance, series resistance is connected across the meter for protection against high voltages in case of series resistance fails or flashover occurs. Okay, for protection purpose, we use a paper gap or neon glow tube or Zener diode with a suitable series resistance is connected for across the meter for protection. Okay. The ohmic value of the series resistance R is chosen such that current of 1 to 10 microamperes is allowed for full-scale deflection. The resistance is constructed from a large number of wire-wound resistors in series. The voltage drop in each resistor element is chosen to avoid surface flashover and discharge. Okay. One thing you need to remember, the voltage drop in the meter is negligible as the impedance of the meter is only few ohms compared to few hundred mega ohms of the series resistance. And this one, the voltage drop in each resistor element is chosen to avoid surface flashover and discharges. A value of less than 5 kV per centimeter in air or less than 20 kV per centimeter in good oil is permissible. The resistor chain is provided with a corona-free terminations. The material for resistive elements is usually carbon alloy with the temperature coefficient less than 10 to the power of 4 degree per degree Celsius. Okay. The material for resistive element, they usually choose the carbon alloy with temperature coefficient is 10 to the power of, it should be less than 10 to the power of 4 per degree Celsius. And the next, carbon and other metallic film resistor are also used. Is resistance chain built with a plus or minus 1% carbon resistor located in airtight transformer oil filled PVC tube for 100 kV operation had very good temperature stability. A resistance chain will be built with plus or minus 1% carbon resistor. It is located in a airtight transformer oil filled PVC tube. Okay, transformer oil filled PVC tube for 100 kV operation. It has a good temperature stability. The limitations in the series resistance microammeter design are power dissipation and source loading, and temperature effects and long time stability, voltage dependence of resistive elements, and next is sensitivity to mechanical stress. Series resistance microammeter built for only for 500 kV DC with an accuracy better than 0.2%. This is what series resistance microammeter. Okay. First you need to draw the diagram for series resistance, microammeter, one series, and ammeter across that protective device. Okay, protective device may be paper gap, neon glow tube, or Zener diode with a suitable series resistor. What is the equation for voltage of the source here? V is equal to higher. In this case, we have neglected the voltage drop. Okay, voltage drop in the meter is negligible because when the impedance of that meter is only few ohms when you compare to other few hundred mega ohms of the series resistance, it is less, so they will neglect the voltage drop of that meter. Next, the ohmic value of the series resistance, how they will choose the resistance value, or how they will choose the resistance. The current of 1 to 10 microamps is allowed for full scale deflection. Like that, they will choose the resistance. The resistance is constructed from a large number of wire wound resistors in series. And the limitations of series resistance microammeter design. Okay, power dissipation and source loading, temperature effect and long time stability, voltage dependence of resistive elements, and sensitivity to mechanical stress. Okay, they are built for 500 kV DC with an accuracy of 0.2%. Next topic is resistance potential divider for DC voltage. A resistance potential divider with an electrostatic or high impedance voltmeter is shown in this figure. This is a figure for resistance potential divider with an electrostatic voltmeter. You can see ESV means electrostatic voltmeter. This is the potential divider. A resistance potential divider with an electrostatic high impedance voltmeter shown in figure. The influence of temperature and voltage on the elements is eliminated in the voltage divider arrangement. They are saying that influence of temperature and voltage on the elements is eliminated in the voltage divider arrangement. In voltage divider arrangement, they will eliminate the influence of temperature and voltage on the elements. Next, the I voltage magnitude is given by R1 plus R2 divided by R2 into V2. Okay, this is what equation for that. I voltage magnitude is given by R1 plus R2 divided by R2 whole bracket V2, where V2 is the DC voltage across the low voltage arm R2. Okay, V2 is the DC voltage across the low voltage arm R2. Okay. With sudden change in voltage, such as switching operations or flashover of the test objects or source short circuit or flashover or damage may occur to the ground capacitance. They are saying that with sudden change in voltage, what happens? Maybe is switching operations, changes in switching operations or flashover of the test objects or short circuit flashover. It may occur flashover or damage may occur to the ground capacitance. To avoid these transient voltages, voltage controlling capacitors are connected across the elements. Okay, to avoid this transient voltage controlling capacitors are used to what? To avoid the transient voltages. Okay, connected across the elements. A corona-free termination is also necessary to avoid unnecessary discharge at high voltage ends. Okay, a corona-free termination is also necessary to avoid what? Unnecessary discharge at high voltage ends. A series resistance microammeter with a parallel capacitor connection for linearization of transient potential distribution is shown in this figure. Okay, a series resistor with parallel capacitors for potential linearization for transient voltages. This is the diagram for that. Okay. Potential dividers are made with 0.05% accuracy up to 100 kV. Okay, with 0.1 accuracy for up to 300 kV, and with a better than 0.5% accuracy for 500 kV, 0.05% for accuracy for 100 kV, 0.1% accuracy for 300 kV, and 0.5% for accuracy for 500 kV. Okay. Next topic is peak reading AC voltmeter circuit with potential dividers. Peak reading AC voltmeter circuit is using capacitance dividers designed by Boulder et al. This is the diagram for that. Peak voltmeter with a capacitor, potential divider, and electrostatic voltmeter. The voltage across C2 is made use of in charging the storage capacitor CS. Okay, the voltage across C2 is made use. The voltage across C2. The voltage across C2 means V2. V2 is made use of charging the storage capacitor CS. Okay. And RD is a discharge resistor employed to permit variation of Vm whenever V2 is reduced. RD is a discharge resistor employed to permit variation of Vm. It should permit the why we have connected means to permit the variation of Vm whenever V2 is reduced. Okay, when V2 is reduced, this should go. When V2 is reduced, then this resistor should permit that resistor RD is a resistor, discharge resistor employed to permit variation of Vm. If any changes in Vm, then it should permit V2 is reduced. Okay, V2 value will be reduced, and RD is a discharge resistor. It will allow to permit variation of Vm. CS is a charge to voltage proportional to the peak value to be measured. CS is a charge to a voltage proportional to the peak value to be measured. The indicating meter is either an electrostatic voltmeter or high impedance VTVM. Okay, VTVM. This discharge time constant CSRD is designed to be about 1 to 10 seconds. 1 to 10 seconds, and this gives rise to discharge error, which depends on the frequency of the supply voltage. They are saying that indicating meter is either an electrostatic voltmeter or it may be high impedance VTVM voltage, high impedance VTVM. This discharge time constant CSRD is designed to be about 1 to 10 seconds. This gives rise to discharge error, which depends on the frequency of the supply voltage. To compensate for the charging and discharging errors due to the resistance, the circuit is modified. You can see the peak voltmeter as modified by Hafele. Okay. Measurement of the average peak is done by microammeter robust modification to compensate the charging errors. This is the peak voltmeter with equalizing branch as designed by robust. Okay. M is a electrostatic voltmeter or TVM of a high impedance, and CS2 is a CS2 is CS1 plus C meter. RD2 is RD1. Okay. Equalizing branch, and here measuring branch. M is a measuring branch and this one is a equalizing branch. Why they will modify that one? To compensate for the charging and discharging errors due to what? Resistance. For that, they will modify and they will compensate the charging errors. Next topic is DC electric field strength meter. In this, there are two topics, that is variable capacitor probe or generating voltmeter, and next is vibrating plate capacitor. First is variable capacitor field meter. If a metallic electrode is kept in an electric field E, the total charge induced on its surface A is given by Q is equal to epsilon A in E is equal to epsilon integration of E dA. If the area of the sensing electrode varies and the variation of the area of the sensing electrode is periodic, then the current flowing through the measuring electrode to the ground is I is equal to dq divided by dt is equal to 1 divided by t integration of dq divided by dt into dt is equal to open bracket q max minus q minimum divided by t. This is what equation for the current flowing through the measuring electrode to the ground. Hence, the average value of electrode field is E is equal to Q max minus Q minimum divided by epsilon naught A into T ampere turns, okay, is equal to Q max divided by epsilon naught AT is equal to I divided by epsilon naught A if Q minimum is equal to 0. Hence, the electric field is proportional to the current I. The arrangement of electrodes is shown in the figure, that is 7.6a. Okay. The arrangement of the electrodes is shown in sensing electrode. The sensing electrode, which is in the form of circular disc, is divided into sectors and shielded by a rotating shutter which rotates at an angular velocity omega. The shutter is driven at a constant speed by a motor. They are saying that sensing electrode, which is in the form of circular, it is in the form of circular disc, and it is divided into sectors and shielded by a rotating shutter. It is shielded by a divided into sectors and shielded by a rotating shutter. Okay. Two opposite sectors of the sensing electrodes are grounded and other two are connected to the ground through a measuring resistance. Okay. Some is connected for resistance ground, one it is connected for ground through a measuring resistance R. Okay, through a measuring resistance R. It is connected for a ground through a resistance. Okay. The voltage across the resistance is measured, and from this the electric field intensity is determined. Okay, they are saying that the voltage across the resistance is measured, and from this electric field intensity is determined. From this we can measure the resistance. Okay, we can measure the voltage across the resistance, and from that we can find out the electric field intensity. The induced current signal voltage is rectified by a phase sensitive detector operating with a suitable phase angle relative to the movement of the shutter and is calibrated in terms of electric field E. They are saying that the induced current signal is rectified by a phase sensitive detector. Okay, it is rectified by a phase sensitive detector operating with a suitable phase angle relative to the movement of the shutter. It is related to the movement of the shutter. Okay, and it is calibrated in terms of what? It is calibrated in terms of electric field. Okay. Next is vibrating plate field meter. This meter consists of a fixed face plate with an aperture, a vibrating plate or electrode is located below the faceplate and is made to oscillate at a fixed rate by a driver motor. This is the diagram for that vibrating plate field meter. In this vibrating plate and mechanical modulator driver, faceplate with aperture. Due to the vibrating motion of the driver plate, a variable voltage V between the two plates. Due to the vibration of the driver, what happens? Due to the vibration of driver, a variable voltage V between the two plates. Okay, a variable voltage V between the two plates. These two plates. Okay. The faceplate and the vibrating plate is generated. They are saying that the faceplate and the vibrating plate is generated. This is essentially a variable capacitor and the electric field E is proportional to the voltage generated V. Variable capacitor and electric field is proportional to the voltage generated V. The instrument is calibrated by a placing it known electric field. The instrument is calibrated by placing it in a known electric field. This is what vibrating plate field meter. Next, AC field strength meter. AC field strength meter is usually measured by introducing a small fixed capacitance probe into the field area and measuring the induced charge on it. Since the electric field between the plates of the capacitor is proportional to the charge induced on the plates of the capacitor and varies because of the variation of the AC electric field, the capacitive current is measured for the field. They are saying that AC field strength meter is usually measured by introducing a small fixed capacitance probe into the field area and measuring the induced charge on it. Since the electric field between the plates of the capacitor is proportional to charge induced on the plates of the capacitor and varies because of what the AC electric field and the capacitive current is measured for the field. Usually electrodes of the field probe are spherical or parallel plates. This is the figure for that. Types of electrodes for field probe: spherical, and this is the parallel. Okay. The charge Q induced on the surface of a conductor in an electric field E for spherical electrode. This is given by Q is equal to 3 pi A square epsilon naught E is equal to K E epsilon naught E. The surface change density over a hemisphere is given by 3 pi A square epsilon naught E cos theta. And integrating over the surface area gives the above value. If the electric field is AC and given by E sin omega t, the current through the probe is given by I is equal to dq by dt is equal to k omega E naught E cos omega t or epsilon naught E cos omega t. The RMS value of the current is proportional to the E. The RMS value of the current is proportional to the E. Depending on the type of the probe, electrode used, the value of K is determined and it is included. Depending of the type of probe, maybe it may be spherical or parallel. Okay. Depending upon the type of probe, we determine the value of K. Okay. And it is included. The current is usually measured through a rectifier meter. The current is usually measured through a what? Rectifier meter. This meter can be used over a wide range of frequencies, but what happens? Must be recalibrated for that frequency. Okay, this meter can be used over a wide range of frequencies, but what happens? Must be recalibrated. Okay, must be recalibrated for that frequency, particular frequency. The accuracy of the meter is about 0.5% and depends on the harmonic content. Atmospheric conditions like temperature, humidity, etc., and the position or location of the meter in the electric field. They are saying that the accuracy of the meter is about 0.5%, and it also depends on what? Harmonic content, atmospheric conditions like temperature, humidity, etc., and it maybe depends on the position or location of the meter in an electric field. Okay. Next topic is measurement of ripple voltage in DC system. It has been discussed in the previous chapter. We have discussed that in first chapter also we have read about ripple voltage, right? Rectifier circuits contain ripple which should be kept low, that is less than 3%. Ripple voltages are AC voltages of non-sinusoidal nature, and such as oscillographic measurement of this voltage is desirable. However, if resistance potential divider is used along with the oscilloscope, the measurement of small values of the ripple delta V will be inaccurate. So, a simple method of measuring the ripple voltage is capacitance resistance circuit and measure the varying component of the AC voltage by blocking the DC component. If V1 is the DC source voltage with a ripple and V2 is the voltage across the measuring resistance with C acting as a blocking capacitor, then V2 of T is equal to V1 of T minus VDC ripple voltage. The condition to be satisfied here is omega CR greater than 1. Okay. This is the figure for that. They are saying measurement of ripple with CRO. The detailed circuit arrangement used for this purpose. Here the capacitance C is weighted for the peak voltage. It is important that switch S be closed when the CRO is connected to the source. They are saying that switch S to be closed when CRO is connected to the source so that CRO input terminal does not receive any high voltage signal while C is being charged. Switch S to be closed when CRO is connected for source. Why? Because CRO input terminal does not receive any high voltage signal while C is being charged. Okay. C should be larger than capacitance of the cable and the input capacitance of the CRO taken together. This is the circuit arrangement for the measurement of ripple voltage V1, C and DC source and load, capacitance and RD. In next class, I will explain about measurement of high voltages, alternating and impulse. Okay. Measurement of high voltages. In next class, I will explain.